so
Okay.
So don't swear.
hopefully useful.
Okay, so yeah, you can start whenever you're ready.
Okay. So I'll try sharing my screen here. You guys are seeing my screen?
We can, yeah.
Okay.
Yeah, let me figure out how to do that.
And you're seeing the PowerPoint.
Yes, sir.
Yes, we are seeing the PowerPoint. I'm just working on my volume, which I don't actually know. There we go. Are you trying to do the volume through that? Nick, can you say something?
Hello.
Still going through my computer. DisplayPort maybe? Can you say something else?
Linear regression.
There we go. We got you.
What a strange thing to say.
Zoom puts their menus in the strangest places.
All right.
All right.
Okay, so today we're going to be talking a little bit about linear regression and nearest neighbors regression, but the context here is developing intuition around model choice, and I'll talk a little bit about why I think it's important to be able to do that. The format of the presentation today is I'm going to do several PowerPoint slides, and then we're going to switch briefly over to a Jupyter Notebook, and then do a recap at the end. So also feel free to interrupt me at any time when you have questions or need a clarification. So I think it's good to start by sort of orienting ourselves about where we are in data science land. So this is my version of a slide that you've probably seen in several places that has kind of to do with the life cycle of a data science problem or project. So we often start with problem identification, and then we begin to collect and clean data. We may do some data exploration, and then return to the cleaning. And once we have a reasonably clean data set, we're going to start with the data modeling process. So that's sort of where we are today. And I've broken down the data modeling process into two sub-steps, the first of which is model choice, and that's our focus today. And the second would be parameter optimization. So a lot of talks you hear on linear regression in particular will have to do with exactly how you find the optimal parameters, and that's not what we're going to be focusing on today. After you've done your data modeling, of course, you perform some kind of model validation. You may deploy the model live if it looks promising, and then continue to monitor its performance. So today we're right in the middle of this process. Okay, let's talk a little bit about the general concept of regression. Regression can be represented this way by this equation, where on the left here you have some number that you want to predict. So if it were a class that you were predicting, that would be a classification problem. This is in regression, you're predicting some number. I'm using x to represent the information that you have available to you when you're making the prediction of y. And importantly, solving a regression problem has to do with finding a function or algorithm f, in this case, that maps x to y. And for the purpose of this presentation, we're going to assume that x is just a single number. A lot of these concepts, or all of them, will generalize to higher dimensions than that, but for the simplicity of illustration, we're going to consider x to be a single number. Okay, so I said that solving a regression problem has to do with finding this f. In practice, how do we actually come to finding f? These are a little bit finer points on the same two sub-steps that I mentioned previously. You first have to make a choice of the form of f, and there are lots of choices available. So linear regression is one of them, nearest neighbors regression. We're going to talk about both of those today. Then there are more complex methods like neural networks and others. After you've made your choice of method, only then do you learn the optimal parameters of f given some training data. And that can involve learning hyperparameters and parameters. And the point here is that the first step necessarily comes first. Now, you of course may iterate, but at least at first, you have to choose F before you can move on to the optimal optimizing the parameters, and only after that will you know if the model is any good. But on the other hand, this second step is the first time that your model sees any data. So it's really only in the second step are you going to know whether the model is working well. And so this is why I'm arguing that it's going to be useful to develop some intuition about what types of models are likely to work well given the data that you have. And this is just an aside here about some of the reasons why developing intuition might be important. So can anybody tell me who painted the painting on the left? Does anybody know?
Not great at art history.
So this is a painting by Caravaggio, an Italian artist. And one of the things that he's known for was directly applying paint to canvas before doing any sketching. And this allowed him to work quickly and produce presumably more paintings than he would have otherwise. And this is a very recognizable painting, and I would argue that it wouldn't be as recognizable if he hadn't produced so many other great paintings. And I'd also argue that you couldn't tell just on the basis of looking at the painting that he didn't carefully sketch things out. And I think that demonstrates a sort of strong intuition about what's likely to work in the end, even before he started painting. How about the book on the right? Can anybody guess who wrote the book on the right? Just guess. What do you think?
Who's written the most books? Stephen King.
I'll go.
Oh my God.
Okay, so again, if this had been written, the exact same book had been written by another person, right? Pete would not have been able to apply this heuristic and say, well, it's probably Stephen King that wrote the book, right? And so, part of his greatness is his ability to work fast. And in fact, he's written more than 90 books, or about 90 books, and I think that this one is his latest. So I think it was Stalin who said that, quantity has a quality all of its own, and that also applies to data science. You want to be able to work quickly, and being able to choose a model that's going to work well initially without having to do a lot of iteration is going to help you do that. So how do we develop this intuition? Let's look at are you guys seeing this window up here, or is that just for me?
We have a window that I've moved around a little bit. It's currently blocking the top corner, but I can move it.
Okay.
It's got...
If it's obscuring something important, just let me know. So
I'll move it.
So let's talk about our first method. So I assume at this point you've seen this equation for linear regression with a single predictor variable. But just as a reminder, as in the case of the general regression task, the y on the left is your target. And then the predictor variable is related to the target by being multiplied by a slope and having an intercept added to it. So I accidentally revealed it just a moment ago, but let's think about, this is a chart with the data currently obscured of height versus age in months in children. And so if you were to guess what this might look like, or what do you think it might look like?
I'm going to guess as the age increases, the height increases until about a certain age where it stops increasing, right?
That's right. And so how about if you look at this particular range of months that we're looking at?
Yeah, it's going to just be, a monotonic increasing relationship.
Right. That's exactly right. So here, within this range of months at least, it looks roughly, certainly, modulo some noise monotonic, and looks roughly linear, I would say. So this is the kind of data where it would be appropriate to apply linear regression. By the way, who can quickly estimate the slope here? Or tell me how you would estimate the slope.
It looks like it goes up by about 2 centimeters every 2 months, 18 to 20, or something like that. 270 to every 3 months, maybe.
Well, the slope over what span of time also for the
Yeah,
overall.
the slope is roughly constant. So if I were to try to estimate the slope, I might do something like this. So take two numbers that are easy to subtract on the x-axis here, like 29 and 19, and then find the rise for those data points. So this is, I'm going to say this is 83, this is about 77. So over 10 months, you go up about 6 centimeters. So 6/10 would be the slope. And who can quickly estimate the intercept here?
You'd have to go back a ways since you don't have 0 on the x-axis.
Okay, yeah, so that's basically the trick. It's not 75, right? If you project it back, it's more like 65. So are kids 65 centimeters tall when they're born,
No,
on average?
absolutely not.
No, right? So what does that tell you about the growth in this other range here?
It's
This
nonlinear.
previous months.
Or it's either nonlinear or a different linear relationship.
Excellent. So that's right. So, and it is nonlinear. So kids tend to kind of explode in growth shortly after they're born, and then it's linear. And sort of the point of going through this exercise is that even though height versus age is not globally a linear relationship, if you're interested in a particular range, like the range between 18 and 30 months, it looks like a linear model could work pretty well. So that's another aspect of modeling to consider when you're choosing a model. Okay, so linear regression has, in the case of a single predictor variable, 2 parameters and no hyperparameters. The 2 parameters being the slope and the intercept. And as we just discussed, it's good for when you expect a predictor to be linearly or at least monotonically related to the target variable. Let's take go through another regression method as a comparison here. So nearest neighbors regression, just like linear regression, you can express the nearest neighbors regression method using an equation, but you can also express it in a series of steps, which I find to be kind of more easier to understand. So nearest neighbor regression works like this. Given some particular x predict for which you want to predict y predict, what you're going to do is to find the k instances of x in the training set, which is a set of pairs of x and y that are closest to x predict, and you're going to denote those as the nearest neighbors. So that's where the method gets its name. Okay. And then, in order to get y predict, you simply average the corresponding values of y from the training set for the nearest neighbors. And that gives you your prediction for y predict. So let's look at a picture regarding how this works. So let's say the blue dots there are training data, and you have a new piece of test data, and the single feature that you're interested in has a value of -1. By the way, can you guys see my mouse when I move my mouse?
Yes.
Okay. So the procedure on the left says that we should go into the training set and find the training data points that have the values of x that are closest to this new point, okay? And that's what's shown with the lines here. Basically, if you start a search outwards along the x-axis, you run into this point, and this point. So those are our, in this case, k equals 3 nearest neighbors. And then in order to know where to put this green star on the y-axis, you average the y values of those 3 points. And so that gives you the location of this blue star. And you can do that for any value of x, the x-axis that you want. So in this case, here are the 3 nearest neighbors, and that's the average likewise here. So this is the basics of how nearest neighbors regression works in one dimension. There are no parameters per se, but there is one important hyperparameter, and that is the number of k, the number of nearest neighbors that you're going to average over to obtain the prediction. And nearest neighbors tends to be good for when you have relatively densely sampled data, so not any big gaps along the x-axis here, but you don't necessarily expect the relationship between the predictor and target to be linear or even monotonic. Okay, so now let's test a little bit the intuition that we've come up with, starting first with just a couple word problems. So if you guys had to choose just between linear regression and nearest neighbors regression for a data set without even seeing the data set for the number of years of corn harvested in the US versus day of the year, which would you think you would go for?
Nearest neighbor.
Nearest neighbors regression, right. Why is that?
Just because I expect that it's not a linear relationship since I have to deal with lots of, seasonality and things.
Right. I personally, I haven't looked this data up, but I personally would expect the number of years harvested to first rise around harvest season and then fall off, right? So this is not going to be monotonic. It's definitely not going to be linear. How about the number of feet run versus time in the middle of a long race?
Oh, that's pretty linear.
Yeah, right. And why do you think I added these qualifiers about in the middle of a long race?
Because when you start, when you end, you probably go a bit faster.
Right, so
Exponentially in some places.
you may accelerate at the beginning of the race, especially if it's a short race. But in the middle of a long race, probably you're going to want to keep a pace, right? And so it's reasonable to expect that this might be linear, unless you happen to be changing phases of the race. So now we're just going to jump over to the Jupyter Notebook. Any questions up to this point? I mean, I assume you guys don't have questions, but I would ask.
No?
Okay. So we're going to look at fitting a couple different data sets using both linear regression and nearest neighbors regression from scikit-learn. So the first thing I'm doing is just doing the necessary imports. We're going to need NumPy. We're going to do some plotting with matplotlib. We've got our two regressors from sklearn. And we're going to look at just one particular metric, which is the mean absolute error, to evaluate the fits. And I set the random seed so that I don't get any surprises when I'm presenting to you guys here. So in a couple of hidden cells here, I've defined two functions, f1 and f2. I'm just going to go through those. And then the next two functions are going to help me create some toy training and test sets. The first is a simple random noise term, which is drawing values from the normal distribution. And the second comes up with a single training and test set for the x values, and then builds two different training and test sets using the two different functions that I defined above, f1 and f2. And to each of the terms, I'm going to add some random noise. And I can specify the noise level as an input here. Okay, so now I'm actually going to call that function, the create train and test set, and have it return our train and test sets. And I've defined a couple of the input variables here above. So we're going to have just 10 training points and 10 test points, and a sort of moderate level of noise. And to begin with, it's always a good idea after you've sort of understood what the data set is to just take a look at the data set. So this is what we're gonna do now. We're just gonna do a scatter plot and plot the x versus the y values for the training set for function 1, f1. So here, it's hard to say if this is just either linear with a lot of noise, but it certainly could be nonlinear, I would say. Let's look at f2. Here again, this could be nonlinear. It looks a little more linear than the f1, maybe. And in this case, we're just going to So I sort of gave away what my bias was, but I'll ask you guys, if this is all you knew about the data sets, which kind of method would you apply to these two different data sets? Just of linear regression and nearest neighbors regression.
So I definitely wouldn't use linear regression for the first one.
Okay.
And I probably would use linear for the second one.
I mean, I might try both for the second one.
Sure, and trying both is always a good option, assuming you have enough time. But let's see how the intuitions are working out here. So what I'm going to do here is I'm going to create a linear regression model for F1 by fitting it to the training data, including the Y for F1. Then I'm going to make some predictions using the test X values, and I'm going to compute the mean absolute error between the predictions and the actual test values, and return the mean absolute error. So 0.43 for the linear regression, and 0.266 for the nearest neighbors regression. So again, this was for F1. So given that this is the mean absolute error, which of these two models fit better?
The nearest neighbors.
The nearest neighbors, right? So intuition seems good there.
And you're just using the first nearest neighbor.
Ah, yes, that's right. So you jumped all the way to the end of one of my bonus questions, but that's right. So let's take a look at these results, see if we can understand a little bit better what's going on. So the blue dots are just the same training points that we saw above, okay? And the orange dots those are the same in both of the two plots. I've now revealed what the test data looks like. And the green dots are what the linear regression model predicted for the orange dots in the case of linear regression and in the case of the nearest neighbors regression. So Brian said that he definitely wouldn't try applying linear regression. You can see that the linear model fits the training data kind of like this, and that does happen to be a very bad fit to the test data. What happens here? So as Lindsay pointed out, I'm just using a single nearest neighbor, and so I'm going to get a green point just by looking at whatever the closest blue point is and guessing the Y value for that. So this is the actual test point here in this case. The nearest neighbor is this blue dot, which is nearly hidden behind there. And because this test X value is so close to that, that becomes my prediction for the Y value. And it's not too far off. You can see that in general, the orange dots follow the green dots follow the orange dots reasonably well. So that's why you end up with a little bit lower mean absolute error in that case. Okay. So now we're going to start working with this second data set here, F2, and we're just going to do the same thing. So in this case, it does indeed look like the linear regression has a lower mean absolute error. So choosing linear regression in that case seemed like a good idea. And we can likewise look to see how this looks. So this is the result of fitting the linear regression, and you can see that the predictions are sort of, it's fitted a line like this, and some of the orange points are a little bit farther away, but for the most part there's pretty good agreement. On the other hand, I have only 10 points here, so the nearest neighbors regression, it's somewhat sparsely sampled the data, and so you do get some relatively large deviations from the test data as a result. So just a couple of questions for you guys. Can you make any guesses about, now that we've gone through this process, can you make any guesses about anything about the F1 and F2, what they might look like? So which one is more linear?
Definitely F2.
F2, right? Okay, so let's take a look. I'm going to unhide these cells. So F1, you can see, I I just put in a whole bunch of non-linear gibberish. Whereas F2, over this range, it does look quite linear. It's not exactly a linear function, but on the other hand, given how much noise there was in the data, it probably would have been hard to tell that it wasn't exactly linear. So that's good. And Lindsay sort of already asked or answered this question, but what could we possibly do to make the nearest neighbors model better?
It wouldn't necessarily help for the second one, at least not for some of the big areas, but yeah, helping the nearest neighbor, like the number of neighbors, probably. It would probably improve the first one from just be looking at it.
Yeah, so I agree with you that it won't necessarily make things better, but it's something that we could try, increasing the number of neighbors from 1 to try to improve the nearest neighbors model. Okay, so let's hop back here and talk about this. So I'm not going to talk in any detail about this. I just wanted to let you guys know that other techniques exist. And they're generalizations of these two techniques that we talked about today. So they go sometimes by the name of local regression, and they combine aspects of linear regression and nearest neighbors regression. And basically they work by, fitting locally the training data points to a set of smooth functions, which are usually polynomials. And in data science and machine learning, these techniques, they're often called LOES or LOES. But essentially the same technique was described much earlier by Savitsky and Gallet, and that's why it sometimes goes by the name of SG filter. And if you see the link that I included to the SciPy documentation, it's called the Sav-Gal filter. Okay, so if you're interested in reading more about methods that combine aspects of linear regression and nearest neighbors regression, I suggest that you look these up. Finally, we'll just do a short recap of, we talked about regression, so it's one of the major machine learning data science tasks that has to do with finding a mapping between a set of predictors and a continuous target variable. So the meta lesson here is that model choice is an important first step in performing regression and in data science and machine learning more generally. The ability to make an educated guess regarding what type of model will work well will make you more efficient and, I would argue, therefore better. And understanding exactly how the models work will help you to do this. Linear regression works well when the descriptors are linearly or at least monotonically related to the target variable, whereas nearest neighbors regression works by assuming that closeness of the descriptors implies closeness of the target variable. And it works well in case of non-monotonic functions. Finally, there are generalizations which you can look into, which combine aspects of both linear regression and nearest neighbors regression. So that's all I have. I'm happy to take questions from you guys.
So why wouldn't you just use the generalized one that uses both?
So yeah, that's great. I didn't say this last sentence out loud, but these generalizations, they too come at the cost of increased computational expense and complexity. And so it's really good to know when you should apply a more complex model and not apply it before it's necessary. In particular, these local regression methods, they get messy in high dimensions, whereas like in 1 or 2 dimensions, they tend to work pretty well.
You have any questions, Pete?
I don't think so. I mean, it also might not generally make sense to be able to like interpolate or smooth between these values, right, with the nearest neighbors regression.
Yeah, I
Sorry.
Pete was just pontificating over like interpolating.
Ah, okay.
Okay, well, I don't think we have any other questions. Are you ready for comments?
Sure.
Okay, anybody want to start?
And tell me if I need to move to a different part of the presentation or anything.
Yeah, can you go back to, it was toward the beginning. Yeah, first of all, I love all this. This is great.
I'm waiting for you to say stop.
One second, I gotta find. Okay, so this is back whenever we were talking about. Yeah, go back to DS Land. That slide. Okay, so we talked about like we're gonna focus on the model choice for what we're doing today. And you said something that kind of stuck out to me. So a lot of what we're doing here is like arguing from like first principles, especially whenever you took us through the age in months versus height example, where we saw like, okay, well locally here we're looking at a linear relationship, but obviously earlier on it's not a linear relationship there. So all those like first principles, you know, kind of reasonings and intuitions are definitely useful. But what about what would you tell the students whenever it comes to, you know, what if they don't have any of that, right? So what if they're dealing with data where they don't know enough about it?
Sure. So yeah, so I would say that it's an important question. You definitely will run across problems where you don't have, as you say, first principle intuitions about the data. And in that case, I would say try to supplement as heavily as you can with visualization of the data.
Mm-hmm.
Because even if you're not able to intuit the relationships before looking at the data, you may be able to notice relationships when you do look at the data. So yeah, I guess that's the most general answer I would give to that question.
Yeah.
If you don't have any idea before looking at the data, then you should take some time to visualize the data in various ways to see if you can directly observe any relationships.
Yeah. Other than that, I don't have a lot. I don't have a lot in ways of feedback to give you. I thought you did a pretty excellent job of your first run through with this. I would say, you know, it might be worth highlighting some of those things a little better, because I think you did it really well with the example you chose too. Because you gave us an example where we're like set up to intuit a linear relationship that does not exist outside of the window we were looking at, right?
Mm-hmm.
Because we obviously know, like in the future, you stop growing. You don't just keep growing like a crocodile the rest of your life. And obviously, like in the early stages of life, you shoot up like a weed. So, but we got to look at this one little window where we saw a linear relationship, right? So I thought it was good. My one little piece of feedback would just be to kind of like maybe highlight the fact that your intuition when you explore data can be wrong and misleading, right?
Sure. Yeah. Yeah, so yeah, always visualize the data in addition to thinking about it.
Pete, you guys have anything to add?
I don't really have any critique.
Yeah, I thought it was excellently done.
Okay, Lindsay's back there somewhere?
I am, and you know I'd ask a question if I had it, so.
Okay.
She fell asleep halfway through.
Do you guys even want him to run through it again with anything? Because I really don't.
I don't know what I would ask to change.
Yeah, I liked it.
Yeah.
Well, you're gonna get high marks from all of us.
Okay. Well, thanks for taking the time, guys. I know I went a little bit later.
Oh, you're fine.
We got started late.
Yeah, that was mainly on us.
Okay, how are things there?
You know,
Honestly, they've been getting better.